Infrared spectroscopy, which is IR, this is a technique that we use in order to determine functional groups in the molecule. So let's say, for example, if we have this alcohol molecule here. This alcohol molecule is made up of sigma bonds. It's made up of a carbon-hydrogen bond here, and an oxygen-hydrogen bond, and a CO bond. So see, all of these are sigma bonds in there. In infrared, bonds vibrate at a certain frequency. If you shine a light on the molecule, if the frequency of the light matches the frequency of the vibration of the bond. Let's say, for example, the bond vibrates, the OH bond vibrates at 5 Hertz. And if the frequency of the light is 5 Hertz, then we have a match here between the frequency of the light and the frequency of the vibration of the bond. Then light is going to be absorbed by the OH bond. When light is absorbed, this bond here is going to act like a spring, and it's going to start to vibrate, either by stretching or by bending. So it's going to act like a spring in this case. Same thing for the CO bond in there, and every different bond has its certain frequency of vibration. This is a characteristic of a functional group. So for example, a CH bond here for an alkane has a different frequency of vibration than a CO bond, than an OH bond. So each one of those have their own frequency of vibration, and if their frequency of vibration matches the frequency of the light, then the bonds are going to start acting like a spring. They are going to stretch, and they're going to bend. And as they do this, the detector is going to detect the signal of the light, because the light will be absorbed, and the detector will detect the signal of the light that is not absorbed, which we call it transmitted, and you will see a signal in the infrared region. So bonds act like a spring, and these bonds, they undergo different vibrations. So this is a sigma bond in there, and I'm showing the sigma bond like a spring in there because sigma bonds, they do stretch and they do bend. And the stretching vibrations, we have two types of stretching vibrations. We have symmetrical stretching, and these symmetrical stretching, they do occur at a higher wave number. And we have an asymmetric stretching, which they occur at also at a higher wave number. So all the stretching vibrations, they do occur at a higher wave number. And then we have a bending vibrations. Now those, they occur at a lower wave number in the IR region. And they are quite a few in there, because when the bonds bend, they can rock, they can wag, they can twist, and they can scissor. Each one of those will have a certain frequency of vibration and will absorb a certain frequency of light. So it's going to show at different regions in the IR spectrum in there. The IR spectrum is a plot of the percent of light that is being transmitted, not absorbed, versus the wave number. The wave number is related to the wavelength, and the scale for the wave number is from 500 to 4,000 centimeter to the -1. Now the spectrum is divided into two regions, and the regions are split from 1,500 centimeter to the -1. So above 1,500 centimeter to the -1, we call this the functional group region. This is where most of the functional groups absorb. And below 1,500, this is called the fingerprint region. And this is where you see the bending vibrations, the wagging, the scissoring, all of those. Every single molecule has specific bending vibrations. And this is why we call it a fingerprint region in there, because this region can identify the molecule. Normally, with our IR interpretation, we don't care much about the fingerprint region. We only care about the functional group region. Unless we are working with benzene, so this is the fingerprint region. Unless we are working with benzene, if we are working with ether, then we would need to look at the fingerprint region. If we are working with esters, we also need to look at the fingerprint region as well. Other than that, we only care about the functional group region instead of the fingerprint region. So we said that every single bond vibrates. And we do have single bonds, we have double bonds, we have triple bonds in there. So if we want to compare the vibration of the triple bond versus the double bond versus the single bond, the triple bond always vibrates at a higher wave number. Higher wave number means in this region here. So because as you go above 1500, you are increasing the wave number. So this is called a higher wave number. So we're expecting that carbon triple bond carbon to vibrate at a higher wave number than a carbon double bond carbon, than a carbon single bond carbon. Okay, now carbon single bond carbons normally they vibrate in the fingerprint region and they vibrate at a lower wave number. Bonds of lighter atoms like hydrogen, for example. So if you have a hydrogen connected to an oxygen, connected to a nitrogen, connected to an sp hybrid carbon, like a triple bond, if you have a hydrogen that is connected to an sp2 hybrid carbon, like a double bond in this case, all of those hydrogens, we call them light atoms. And those light atoms are going to vibrate at a higher wave number. So I would expect that their signal to be in the region which is above 3000 centimeter to the -1 in this case. This table here comes in handy and it shows the lighter atoms where they should be in the region of the IR spectrum. So you have your fingerprint region, which is below 1500. So all of this is going to be our fingerprint region below 1500. And then above 1500, we have the functional group region in here. Between 2500 and 4000, this is what we are looking for in there. So if you have any CH stretch in there, check the hybridization of the carbon and you can know what type of functional group you have. You can know if you have a triple bond, a double bond in this case. If you have an OH, then it should show if you have an NH. NHs can be primary amines, secondary amines, so they all show in this region. Now, triple bonds, they don't have lighter atoms, so we expect them to vibrate at a lower wave number than lighter atoms, but still they vibrate at a higher wave number compared to a double bond, compared to a single bonds. Single bonds, they do vibrate in the fingerprint region. Now on eCampus, I posted 2 IR tables, absorption tables, and this is going to be the first IR absorption table. It contains almost all the functional groups. And there is a second IR functional group table also. It is the same, but there are sometimes there are some functional groups that are found in one table, they are not found in the other. So you can use both of these tables in order to interpret the IR spectrum. Here, I do have in the notes, I do have the IR spectrum for various types of functional groups and how it's supposed to look like and what you need to look for. So if you have an alkane, alkane is not a functional group. This is, for example, hexane. It's all made up of an sp3 CH stretches. Every time you see an sp3 CH stretch, that needs to show in the region between 2850 and 3000 centimeter to the -1. It needs to look like that. So this is the carbon sp3 CH stretch. For the alkene now, for the alkene, for example, here 1-hexene has sp2 hybrid carbons, and it does have a hydrogen over here that belongs to the sp2. And it does have 2 hydrogens over here that belong to the sp2. So these are carbon sp2 hydrogens. All 3 of them are carbon sp2 hydrogens. These are lighter atoms. So the hydrogen is a lighter atom connected to an sp2 carbon. So I'm expecting this to vibrate at a higher wave number than the carbon sp3 hydrogen in there, than the carbon double bond carbon. So if you have an alkene, these are what you're looking for. You're looking for the carbon double bond carbon, which is a strong and it is a sharp peak. You can see that it is a sharp peak and it is a strong peak in there. And that peak is going to be at around 1650 centimeter to the -1. Sometimes it occurs at 1640, sometimes it's at 1620. So it's not necessarily 1650 exact. It depends on what the alkene is connected to. And then any alkene, if it is at the end, meaning it's terminal, then it needs to have hydrogen. Then you need to look at the carbon sp2ch stretch. And it needs to look like that. And it needs to vibrate at a higher wave number than the carbon sp3ch stretch. Notice that the sp3ch stretch is found in every single structure if you have a CH3, a CH2, or a CH that are sp3 hybridization. If you have a triple bond, then what you're looking for is the functional group itself, which is a carbon triple bond carbon. If the triple bond is at the end, and then you would need to look for the sp-CH stretch. And the sp-CH stretch is normally a strong and a sharp peak that looks like this. And it vibrates at a higher wave number than the carbon sp3 hydrogen, than the carbon triple bond carbon. The carbon triple bond carbon always occurs at this region in here. So it is a sharp and it is a small peak, as you can see there. So if you see anything like that, small sharp in this region, this is immediately a triple bond. Also, if you can go ahead and do the DBE of your structure, and if your DBE is equal to 2, then definitely you have a triple bond in there, especially if you have a peak in the IR region at around 250. For alcohols, OHs, they have a broad peak in there, whether they are primary, secondary, or tertiary alcohols. This is a secondary alcohol, but it doesn't matter. Always OHs, they have a broad peak like this. And this is the vibration of the OH. Hydrogen is a lighter atom, so it's going to vibrate at a very high wave number in there. So it's going to occur the first signal in the IR spectrum. Then, of course, you have the sp3ch stretches over here, and pretty much that's it. You don't have anything else because your structure is only made up here of an OH functional group. The others are the sp3ch stretch because it's made up of CH3s and CHs and CH2s. Now you might see the CO stretch since we have the OH over here. This is my hydrogen and then the rest of the molecule. Then the CO stretching is going to occur in the fingerprint region. This is the CO stretch in here. So it's going to occur in the fingerprint region, and it's going to show around. This is going to be around 1,000. This is 1,100 over here. So that is the CO stretch of the alcohol. We don't care about the CO stretch in the bending region. So this is the fingerprint region in here, because we can identify the alcohol in the functional group region. So if you can identify a functional group in the functional group region, no need for you to look for any identification of that group in the fingerprint region. But as I said, there are some functional groups that are not indicated in the functional group region, so you have to look for them in the fingerprint region. Something like ether. Ether is not going to be shown. So the CO bond of the ether is not going to be shown in the functional group region. In the functional group region, you're only going to see the sp3 CH stretches of the carbons and hydrogens. That's it. So to look for the CO bond, you have to look at the fingerprint region, and it should show at around, it is a sharp peak. It is a sharp peak, and it should show around between 1,100 to 1,200 centimeter to the -1. That is the vibration of the bending vibration of the CO of the ether. For carbonyls can be either aldehydes, ketones, carboxylic acids, esters, amides. So it really depends on what you are looking for. In general, carbonyls, they do absorb in the region between 1600 to 1900 centimeter to the -1. So this is the region here. And in this region, this is the region only for the carbonyl. So it's in the region between 1600 to 1900 centimeter to the -1. This whole region here is for the carbonyl. There is no other functional group normally that absorbs in this region and there. So this is a characteristic for a carbonyl. And to know that you have a carbonyl, carbonyls, they are sharp, they appear sharp, and they are very strong. So you're going to see a signal that is very long and it's very strong in this wave number in here. So this is immediately a carbonyl. Now, a carbonyl for the ketone occurs around 1700 centimeter to the -1. If you have an aldehyde, then you're going to see it at around 1720, 1730, 1740. So it's actually above 1720 centimeter to the -1. However, there are in the aldehyde in particular, there are two characteristic peaks in the aldehyde that differentiate that from the ketone. Because we know that aldehydes are carbonyls connected to a hydrogen. So you will have an sp2ch stretch in there, two peaks for those. So aldehyde has this characteristic, which is different than the ketone. And this can differentiate the aldehyde from the ketone. By looking at this region and seeing those two peaks, immediately you would know that this is an aldehyde. For carboxylic acid now, hexanoic acid, for example. Carboxylic acids, they combine between two things. They combine between the carbonyl and the alcohol. Okay? Now, because they combine between two things in there, you're not going to see a separation between the OH because we've seen how the OH looks like in the regular alcohol. The OH is separate or it's separated from the sp3ch stretch of the alkane. So this is the sp3ch stretch, and there's a distance separation between the alcohol peak and the carbon sp3ch stretch of the alcohol. In case of the carboxylic acid, you're not going to see that separation. So you're going to see the alcohol peak in here. So this is going to be the OH peak in there. So this here is going to be the OH vibration peak. And the OH vibration is going to be between 300 and 500 centimeter to the -1. And that is going to directly be fused to the carbon sp3ch stretch in there. So you're going to see all of this. This is going to be your OH stretch, and you're going to see your CH stretch as well. And this is the characteristic of carboxylic acid. There's no resolution between both peaks in there. In addition to the carbonyl, so immediately you would know that you have your carboxylic acid. We said that every bond, when it stretches, it bends, and the bending is going to show in the fingerprint region. But if you can identify the functional group in the functional group region, no need for you to look in the bending region. So I don't need to look for the OH bending because I already know the OH is stretching there. For the CO stretch in here, also no need for me to look for that. And for the OH bend, there are two OH bending in there because we said that bending can be wagging, twisting, scissoring, and each one of those will show a peak in the fingerprint region. Although I'm identifying all of those, but you don't need to identify any. Esters have a molecular formula of an RC double bond O and an O and an R. The R is an sp3 hybridization. So this is a carbon that is an sp3 hybridization in there. So I am looking at the following functional groups. I am looking for the carbonyl. And the carbonyl is, as we said, the longest peak in the spectrum in there. And I am looking for the sp2co stretch. The sp2co stretch here, it's going to occur. This is the sp2co stretch. It's going to occur in the fingerprint region between 1300 and 1000. And it's going to look like that. So these are the sp2ch stretches in there. It's around like 1200 centimeter to the -1. It's a broad. It depends on what the ester is connected to. What's the CO connected to? Basically, it depends on the R here and the R there. Of course, you have in this structure the sp3ch stretches that also you need to look for. And there is also another type of a CO stretch that it occurs at in this region here, which is the sp3 CO stretch. So the sp2 CO stretch occurs at a higher wave number than the sp3 CO stretch. We have two types of CO stretches. So this one here is the carbon sp3 CO stretch, and this one here is the carbon sp2 CO stretch. Amides, there are different types of amides. There is a primary amide, there is a secondary amide, and there is a tertiary amide. Now, tertiary amides will not show any sign of absorbance in this region in here. So you won't see any absorbance here. But primary and secondary amides will, depending on the hydrogens that they have. So primary amide has two hydrogens in here. So you're going to see two NH stretches. And those two NH stretches in there, you're going to see them in this region, 3200, 3400. Of course, there's the carbonyl, and you're going to see the carbonyl of the amide. It does have a certain characteristic and 1600 in there. There is definitely the NH stretch, the carbon CH stretch in there. The NH stretch occurs at a higher wave number. The CN stretch in there, it occurs at a lower wave number and in the bending region. So it's going to be around 1390. So this is what you would need to look for the amide in there. There's a difference between primary amide and secondary amide. Let me go back. So if you have a secondary amide here, then instead of seeing two peaks, you're going to see one peak because a secondary amide has just one hydrogen next to the nitrogen. So you're going to see just one peak for the amide. For the amine, same idea. Amine doesn't have a carbonyl. It's just NH2. It's an R NH2 in there. And we have two types. We have primary amine. We have a secondary amine. We also have a tertiary amine. Tertiary amine will not show any NH stretches because it doesn't have. But the primary amine will show two NH stretches in this region, and they will show between 3300 and 3400, and secondary amines will show just one NH stretch in this region over there. For this structure, you only have the carbon sp3 CH stretches, and of course you have the CN stretch. This one is going to be in the bending vibration. Nitriles, they are similar to triple bonds. So as the triple bonds, they did occur. They were sharp and strong peak at 2,250. Also nitriles, they do occur at 2,250. So you got to look at your molecular formula and see in this case, because both have a DBE of 3. I'm sorry, 2. Both have a DBE of 2. So a triple bond has a DBE of 2, and the nitrile is a triple bond, so it has a DBE of 2. So you have to look at the molecular formula and see if the molecular formula has any nitrogens in it. So if you have a DBE of 2 and your molecular formula has a nitrogen in it, then you have it nitrile. If not, then you have a triple bond, a simple alkyne. For this structure, I have the triple bond, and then I have the sp3ch stretches. I don't have anything else. Let's say if I have the structure and I want to interpret its infrared spectrum, then I would need to look for the functional groups. This is a benzene. It is a carbon double bond carbon in there, so I am looking for the sp2ch stretches. This is the first thing that I need to see in there. The hydrogen is a lighter atom. So here I am looking for the sp2. Carbon sp2ch stretches in there. I would also be looking for the carbon double bond carbon stretch. So I'm looking for the carbon double bond carbon stretch. And I would need to look for the carbonyl of the aldehyde. And I also need to look for the sp2ch stretch for the aldehyde. And we said that these are two peaks in there. So we need to look for the sp2ch stretch of the aldehyde. So these are the three things that I would need to look for. Starting from the carbon double bond carbon of the benzene, if you look at the IR tables posted, whether this table or the other one, it really doesn't matter in there. So for the benzene, you're looking at the region between 1600 and 1450 in there, and this is the carbon double bond carbon of the benzene. So whenever you see a sharp peak at 1600 or 1580, this is going to be the carbon double bond carbon stretch of the benzene. It's the symmetrical stretch. We care about the symmetrical stretch in there more than the asymmetrical stretch, because there is a symmetrical, there is an asymmetrical. So let's focus on the symmetrical stretch. It will be in this region. It is going to be a long and a short peak. So this indicates that I have a benzene, a carbon double bond carbon of the benzene. And then the sp2ch stretches, those are going to be occurring at a higher wave number as we agreed, and it's going to be in this region in there. As with respect to the aldehyde, if you have an aldehyde in there, then you're going to see the carbonyl of the aldehyde, which is between 1750 and 1625, and then the two CH stretches that we've talked about. You're going to see those as well. Okay, so I think that we covered all of those. We don't have an sp3ch stretch in here. There is no CH2s or CH3s in there, or even carbon sp3chs. So there is no carbon sp3ch stretches. There is only carbon sp2ch stretches in there. So these are the carbon sp2 for the aldehyde. And those we expect them to be separate from the carbon sp2s of the benzene. Okay, the carbon sp2s of the benzene will occur or will vibrate at a higher wave number than the carbon sp2s of the aldehyde, but they will be close to each other, very close to each other.